today Naga and I, both of us, are going to talk about something we have not really worked on at all. So this was as much a learning process for us as hopefully it will for you. So yeah, the topic is fairness in machine learning. And before we even delve into this topic, it's important to understand why we are even talking about this. And the reason is that machine learning algorithms are being used widely across several fields, especially even in governments, for instance, in policing, by credit rating agencies and so on, to determine who to give loans to and who not to give loans to, recruiting to even at least first cut off a bunch of resumes before it goes to the next level. Similarly, advertising, which offers to make to which person, as like offers also become more personalized. For instance, credit card offers, which offers to make to which person and so on. So all of these, many of these areas right now are being influenced by machine learning algorithms, and machine learning algorithms are being used to make decisions regarding these. However, traditionally, all these, most of these aspects have anti-discriminatory laws, where, for instance, in policing, for instance, how do you determine so in the US at least, for instance, when a prisoner comes for parole, there is a parole officer and he puts all his data into this parole system, and the parole system says what is the risk of this person committing another crime if he is released. And if this algorithm, unless we understand how this algorithm works, we cannot really say that we are being fair to all prisoners in terms of whether we are releasing the prisoners who are less likely to commit a crime and not releasing prisoners who are more likely to pre-commit a crime. So so when all these things are done traditionally, there are laws to address how we can maintain fairness and equality and all these other notions that we find important in these areas. However, when we are using machine learning algorithms to do this, it's not clear how we can automatically enforce all these aspects that we believe to be extremely important. So let me start by the first example, which is the predictive policing. So as I said, in the US, one is the parole system, where the decision whether to parole a prisoner or not is based on an algorithm. Another thing, for instance, is while predictive policing, for instance, there may be some areas which are more likely to have a crime being committed in that area, and there are some other areas where crimes might be less likely, and people are using police are also using a lot of data aggregation and so on to be able to position their resources. So there is limited amount of resources, which is policemen, and you want to place them in a bunch of in places that are high risk, and you are using algorithms to figure out what are these high risk areas. So inadvertently, you might be providing more safety to some citizens and less safety to some other citizens, right? The second one, for instance, is how you actually do underwriting. So let me just play this video.
Is your lending business leaving money on the table? The answer is probably yes. That's because traditional underwriting can miss many deserving borrowers. It uses only a handful of data points, 50 or even fewer, to produce credit decisions. But a lot more data is available to help you make informed credit decisions about the millions of millennials and other underserved consumers around the world. How do you make sense of all that data? Machine learning. Machine learning can provide accurate, predictive analysis based on thousands of data points. Within seconds, you can make solid credit decisions about thin-file borrowers, the ones that traditional underwriting models can't serve. But if that's the case, why has machine learning so far had little impact on underwriting? For one, machine learning models have historically been black boxes. It can be nearly impossible to get full visibility into how those models work. And time is money. It takes a lot of both to transition from traditional to machine learning underwriting. We know. We built our own machine learning underwriting technology. We've been using and refining it for years. And now?
So I just wanted to play this brief slide to give an idea of how people think about machine learning in, say, the underwriting business, which is basically giving loans. even though they basically try to say that we try to make machine learning algorithms that are more not black box, you can at least you get the feeling that they are still somehow using machine learning in a more black box way, the way they say machine learning like 5 or 6 times in the 1 minute video. So so this is another example where it's important to understand what is the basis of the decisions that you are making in terms of accepting some loan applications and rejecting some other loan applications. So another example is again this recruiting that I just mentioned. So we can just read this exchange. So HBR is a reporter and DeStefano is a recruiting company. So the reporter basically asks how a particular tool that DeStefano has developed works, and the representative from DeStefano says that basically they ask the company which wants to recruit a new chief of staff what exactly are the requirements that you want from the new chief of staff, and that company tells DeStefano that we need this person to have these skills, and then at the end they also ask them what exactly does the person actually need to do, and then they say that they have an algorithm that takes all this together, crunches it, and then comes back to us with the profile of the person we are looking for. So it's completely clear how black box the algorithm that they are using is, at least the way they are using it. So coming back from these examples, so let me first introduce 2 legal concepts of bias. Okay, so the point is there is a legal concept for fairness which is in law and so on, and we are trying to apply that to machine learning algorithms. So we should first try to understand what exactly are the concepts in the legal world, which what we mean by fairness, what is equality, what is justice, and so on, and then try to see how we can actually apply them to machine learning models. So let me first introduce what the legally bias and fairness means, and then we'll go back to machine learning frameworks and see how these can be actually converted into some numbers or some notions that you can actually verify whether algorithms satisfy these or not. Okay. So the 2 legal concepts, so this is according to US law. The 2 legal concepts of bias in the US law are disparate treatment and disparate impact. So disparate treatment is basically which is unfair right in the face, which basically says that these people, so you are explicitly favoring some people over other people. Examples include restricting employment, for instance, based on either caste or religion, or pay difference between men and women at the same position. Like these are completely unfair right on the face of it. And the main point here is that similarly situated people who have the same background should be treated similarly. So you should not really distinguish the 2 of them. On the here the focus is basically on the individual, and that's what I say when I say that similarly situated individuals should be treated similarly. On the other hand, there is another notion called disparate impact, which is kind of a more subtle way of being unfair. So on the face of it, it does not seem unfair. For instance, if I am renting a house and I want the incoming person, the person who is coming to rent, to pay a lot of advance, on the face of it, anybody can actually come and pay me the advance, but only people who have enough money will be able to pay me the advance. So even though on the face of it, I am being fair to everyone in the sense that I am giving the same rule to everyone, only some people actually are able to comply with that and many other people are not. So this is a case of disparate impact, and basically this says that, for instance, in recruiting or employment or these kind of things, disparate impact is classified by saying that whatever requirement you have should be completely job related. If you have a requirement that's not really job related, even though it may seem uniform for all the employees, it's not, it amounts to disparate impact. Yeah.
So this particular example that you gave,
yeah,
doesn't actually seem bad, or are you saying this is bad? Like this particular example, you want to rent a house, you have to pay me this much amount.
So okay, so in India, it's fine in the sense that you actually earn interest on this advance. So that way you might justify that, but the broad thing that I'm trying to make is, for instance, in some companies, if you want employment, you'll have to pay money before you join, and that need not be. So wherever there are business requirements, or you are actually making use of that money, or you are gaining out of that money, you could give a business reason for actually having that rule. But cases where you don't have a business necessity, but you are still imposing these kind of rules just to cut off a section of population, that's disparate impact.
Because like if you have to, I'm just saying that if you come to Bangalore, you might be earning a decent amount of money, and you know whatever, and but you might not have 9 lakhs to give as a 11-month deposit, right? And if that is the requirement, it does do a kind of cutting of edges.
No, but my question is like again, I mean, when there's also a public space, private space here, right? Like if I am the owner of the house, like should I be allowed to make my own decisions or?
No. So still there are anti-discriminatory laws. Like you cannot make those decisions based on caste or religion, right?
Fair enough. Which is why I'm asking.
In India, possibly there are not such.
I'm actually not saying one way or the other. I'm actually asking you, is this bad according to your
This
definition
is
of
fine
impact?
because you are making money on the interest. So the person who is renting the house can argue that I need it for my money. There's a business goal for it, like he said.
No, I completely understand what you're saying. So I'm not.
No, but so
saying
I
that-
actually want to ask a different question. Like, so what is a justifiable business goal? Like, can't business goals be discriminatory? Even goals can be discriminatory.
So I don't know. I think even courts do not really agree on what could be termed business
Yeah, actually,
necessity
these
or
laws
not.
are primarily drafted with employment context. Like, if, for example, if you actually if you have an SN in the US, you would have gone through some of these exercises. Like, you would log in and make sure that you understand what this treatment is in practice with respect to university and so on. So I don't know if this.
Yeah.
this
So
can broadly apply,
one of
but-
the cases that involve disparate impact, for instance, is that some company in the US had a particular entrance test or aptitude test for people for their employees, but their employees were basically had to do manual labor. So an aptitude test was in no way necessary for the employees to perform their duty. But then apparently it had the impact that people white people were had more education or something, and then they were able to more white people were able to pass that aptitude test as compared to black people. But the court ruled that that's illegal because that's not really required to do, for the employees to actually perform their duty. So on the face of it, having an aptitude test seems like completely fair, but that had nothing to do with the duty that the employees had to perform, and it was basically cutting off section of the population. So this is basically what's disparate impact. And I wanted to give an example which is more in the context of India. And gentrification, I feel, is one of the things that actually happens, and is different set of people living in different areas.
So like you have a posh area where ghettos of poshness and ghettos of non-poshness, and it happens, right? Like it's
9-month deposits.
9-month deposits and push the more normal population out, right? Of a lot of areas.
So just to conclude, this you're saying this is unfair. Like the example that you have listed here.
Yeah,
can be
personally I
unfair.
feel
Two unfair notions, right? One is unfair ethically, one is unfair legally. I think that's not legally unfair. It's
Ethically
ethically,
Ethically
it's
unfair.
very subjective.
Depends on what ethics you have.
yeah.
Can you just elaborate on these anti-discriminatory laws that you said? You said a person while renting the house can't choose based on say caste, religion.
So I'm not fully sure if that's a law in India or not.
It is actually a law in India, but nobody actually enforces it, and it happens. I mean, it happens all the time in Bangalore. That
Not just Bangalore.
No, all over India. Yeah.
No, in Delhi it doesn't happen.
Oh,
Yeah, but then
at least many other places in India.
So like in cosmopolitan places, Bangalore actually say places like Malleshwaram and all. If you're a non-Brahmin, getting to places like
I was thrown out of my.
yeah, but it's not
My list explicitly states that I should not put non-vegetarian in my house.
Yeah, things like that. So it's actually illegal. Bombay, for example, they're always having these issues. So So, but
Okay.
it is the law legally it is not. It is illegal.
So how are these laws framed is all I'm asking. Like, what do these laws kind of say? How general is it? How do they like talk about discrimination? I'm just saying.
Yeah.
Just continue.
So let's take the questions at the end maybe, just for the sake of time. Okay. So let's come to now the question of fairness in machine learning, and before we even come to this question, we should ask ourselves why machine learning algorithms can actually be unfair, and there could be multiple reasons for why machine learning algorithms could be unfair. The first reason is that data might actually encode existing biases. For example, you want to predict whether a prisoner, if released, is going to commit a crime again, but you don't have information in the future. All you have is information in the past, and you have to make use of that information to predict this. So that may already have, so let's say in the past only a section of people were paroled more often than other people, then you tend to basically fit a regressor or something to past data, and that would basically encode existing biases that have been of decisions that have been taken before the system was actually put in place. The second one, for instance, is data collection feedback loops, which is that you only observe one, so you cannot ask you don't have counterfactual data. So in the past, I have been doing this, and this is the data. I don't have data on what if I had done something else differently. So I have this group of people. I gave loans to some people, and I can only observe what happened to those people. If I had not given loan, or for instance, if I had not given loan to these people, I don't know what would have happened if I had given loan to these people. So data, both in terms of existing biases and like this lack of counterfactual data, could cause the machine learning algorithm to encode biases that were previously there because of human actions. The third one is a little more subtle in the sense that different populations could have different properties with respect to the same parameter. So let me give an example. So there is this green population. The y-axis is basically the SAT score or some kind of, and the x-axis corresponds to whether they have a credit card or not, or the number of credit. So the x-axis corresponds to the number of credit cards, and then the plus is basically that they are paying on time their credit, and the minus basically says that they don't pay back their loans on time. Okay, and a credit card issuing company wants to make use of this data to figure out whom to give credit cards to and whom not to give credit cards to. So if you just look at the green people, then basically I have a classifier which tries to classify the people who pay back their loans and the people who don't pay back their loans, and then the classifier will say give all the people above this blue line, give them credit cards, and the ones below don't give them credit cards. Now let's say there is a second group of population with this kind of distribution where the SAT scores are generally lower, but even among them there are people who actually pay back their loans, right? Now when you combine both of these, if you just fit a single classifier to the entire data, it turns out that people in the orange population, even those who actually pay back their loans, will not end up getting the credit card, right? And this seems totally unfair for the people in the orange population, because basically no one who can actually pay back loan, even people who can actually pay back the loan in their community, are able to get these loans. So okay, so this is what we meant when we said that different populations could have different properties. So if you try to do one size fits all kind of machine learning model, it might be unfair to a certain class of population. However, another thing that we could have done here is basically that we could have chosen two different classifiers, one for the green population and another for the orange population, which might have been fair within each group, but then that intuitively also seems unfair, because people in the green population who are maybe positive, like someone here, so let's say this guy will feel that he has a better SAT score and has prepaid loans on time, but then this guy gets the loan, this guy gets the credit card, and this guy does not get the credit card. So people in the green who actually pay back their, so in either case, it seems like we have some unfairness issue no matter what we do. So the final thing is that is very similar to the feedback loops, which is that by definition, the minority population, we actually have less data. So whatever models that we build will be more uncertain about the minority population than the information that we have about majority population. So any model that we actually end up fitting might be unfair either to the minority population or unfair to the majority population. I think Naga will take over for now for a bit.
Yeah, there's actually one point that I would like to emphasize in this slide. So if you think that the natural strategy to deal with this problem is to just is through blindness. Like, let's say I will completely ignore the race or the color attribute here and try to build a model. But then clearly that doesn't help because, for example, I will arrive at the same classifier no matter I feed in the algorithm the color of the label, the color of the population or not, right? So this sort of also serves to illustrate that fairness through blindness is not a strategy. So moving on to how we might actually formalize these notions of fairness and how machine learning community as a whole has tried to mitigate these issues in real data. So the first notion of fairness is statistical parity. It talks about how the algorithms should not prefer a certain group over the other groups of people. So let's say let X be the set of all individuals, and let's say there's a protected group S, and this protected group could be something like a community, or it could be some sensitive features in the data. So for example, you might not want to distinguish, or you might not want to favor the outcome of the algorithm based on certain attributes of the data. So you might explicitly filter them out, and then you can, let's say, call them S. So S is a set of all population that actually have the sensitive attribute turned on, let's say. And what do you like for the classifier to have? So it better have this property that the favoring of outcome by the classifier should be sort of unconditionally dependent on the particular group that you have selected, protected group. So even if you condition on the protected group, your favoring of the outcome for this particular event that you care about should not change. So that's a very fundamental notion of fairness that many people can relate to. And
when you say min bias, bias is 0, then that's the ideal situation.
The ideal situation, according to this metric of fairness. Yes. So typically, so for example, in this example, what we minimized was just the error rate, right? I just looked for the probability that h of x, which h of x is the prediction by this line, h of x not equal to y, the true label. So that's the only metric I cared about. But if I want to also introduce fairness, then I might consider a metric like this. And here is one example where this statistical parity is clearly compromised. So the professor, Latanya Sweeney, is a professor of government and technology in Harvard University. So this was actually, this made big news in around 2013, I guess, where she basically brought Google AdSense to lawsuit, and she figured that depending on the queries you make on Google search engine, if you made queries that had actually white people names versus black people names, she found that one search result had disproportionately higher number of arrest type ads than the other population, than the black ones. So yeah, so I think there's an 80% of black name searches, but fewer than 30% of white name searches led to ads that actually had arrest in them. And she's a person of color herself, and that sort of naturally, I guess, enraged her, and she actually went ahead and wrote this big article, and it made a lot of news and so on. And so basically her worry is that this racial bias could sort of go on to affect the people's chances in employment, and because ads are not an end product by itself, right? Because ads also enable employment, ads also enable businesses, money, revenue, and so on, right? So just if you make one bias in the search engine, it could lead, this ripple effect could lead to other places of as well, in terms of employment or businesses and so on. Actually, this is a nice article. Yeah. So this is another company called Text.io. So they actually, it's a sort of funnily positioned company, given that there's LinkedIn and other companies that actually are big on recruiting. So what they do is that they enable this platform for advertisers, as well as I believe for people looking for jobs. So where they ask people, like say you're a person from HR, you go to this site and write down this ad for a role. For example, in this case, there is general market media buyer, and you fill out your advertisement, right? Like what do you want, what do you expect of the candidate? And then it's after this, it does some analysis on this. So for example, it identifies some certain blue words, and then it sort of says that these blue words sort of indicate a masculine tone. So it comes up with I believe it has a lot of benchmarks of advertisements, and then it crunches through this, and then comes up with something called a Text.io score. It says below average for this particular ad because I guess it's very the tone of this is not nice. It says it needs more restatements and missing equal opportunity statement. So you can clearly see, for example, so this is the sort of interesting thing that it actually can identify the tone of the person, or I guess by masculine tone it means that it probably hints at looking for candidates that are men. Right? So it sort of says that you should not do that, or and this also sort of encodes the biases in the data that say that typically people looking for male candidates write posts like this. So this is another case of reinforcing statistical parity. Another notion is individual fairness. So moving on from the sort of community or group level to individual level. So here the notion of fairness is that if there are two individuals that have very similar merit, then your prediction for outcome, the favoring of outcome for the individuals should also obey that merit in the real world. So this D is something that the real world throws at you. It could be tasks. So for example, this D could say that these two people are reasonably fit for the given job. So this D is a metric that is typically unknown to you, and it's sort of chosen naturally for the task. And if H is a classifier that you are trying to build, and I want to compete with this metric that I don't know, that I don't observe necessarily in the real world, and I want to make sure that my predictions are similar if these people are similarly situated in the real world. So we'll see another example in detail for this particular notion of fairness. Another one is equality of opportunity. So here it says that there's a protected group, and so here what it says is that so if the person is truly qualified, if the person is truly qualified for the outcome and belongs to a protected group, then your outcome should not adversely change based on the membership of the protected group or not. And so here is a nice example that serves to illustrate. If this is a show that comes on AXN called The Voice. So they actually they conduct these blind auditions. So where clearly you see what the blind auditions are, right? So at least this helps favoring certain aspects, right? Though I'm not really sure. I guess voice is usually revelatory of color as well.
So is this like the looks will not matter?
Looks, yes. This show is heavy. I don't know if you have watched the show. This heavily relies on looks. So it's a show, yes. And so there's a company called Gap Jumpers. They sort of try and mimic this model. They say that we will not look at just the resume, the words in the resume, or how you speak, how you have written things, how you have formatted things. So they come up with inventive ways of recruiting. They say that you can upload a speech, like you can upload your own notions of evaluations, and they also come up with some notions of evaluation. One is speech. They say that you can upload an advertisement, or you can upload how you think you qualify for the role, and then they sort of do mix and match, not just with the text data, but also with different forms of data that sort of can mitigate some of these biases. This especially with the notion of equality of opportunity. And the final notion is predictive parity. It's a slight variant of the above. So if you look at it, it just flips the notion. So this basically says that if your algorithm has favored a particular set of candidates, then it better be true that in the real world that's the case, no matter whether the particular set of candidates came from a protected group or not. So it's a slightly different version. So these are different. I'm not even sure if this is exhaustive. I'm sure people come up with different metrics. And the whole point is that many of these goals are fundamentally at conflict with each other. So there is a recent archive paper by Kleinberg and his colleagues, which says that certain notions of fairness are fundamentally in conflict. So in particular, he picks three fairness conditions. These two are basically equality of opportunity. This is equality of opportunity with respect to the positive class, with respect to the negative class. And this is another notion of statistical parity. So basically, you want to say that in a protected group, if you qualify some people for the outcome, then in reality it should match. That, for example, in the classifier, learning a single classifier example, this will be violated because for the orange group, this was 0, whereas in reality it was 0.5. About half the members of the orange population were able to repay the loan. Y is reality. Yeah, sorry, I didn't. Y is reality and H is algorithm's outcome. This paper argues that if you ask for an algorithm that simultaneously satisfies all these three constraints, even a sort of relaxed, because this is not exact equality, so even if a slightly relaxed version of these constraints, it is impossible to meet unless you are in a very restricted setting. For example, if the labels are always deterministic, like you know that, let's say there's a clear separable decision surface, unless you are in those uninteresting cases, you can prove that these three conditions cannot be met simultaneously. So invariably, you end up choosing one or two, which you think is fair for the particular task that you have, and you may not be able to simultaneously satisfy many people. So this is the point of the article. This is an interesting paper. It's a fairly recent paper. So now, let me walk you through a very simple problem that's been done to death in online learning, machine learning field.
So in the examples that you took, the outcome, it was a binary classification task.
Yeah, that's representative. It can be regression and any classification.
Does it become easier if it's a spectrum or
no?
Equally?
You can define all these metrics with respect to any outcome that you have. The outcome can be categorical, the outcome can be real valued, the outcome can probably even be structured or anything. So all these notions of fairness will still continue to hold.
Another question. There's also, this is, I think, slightly meta, in the sense, there is if you take the credit industry, right, from the example that you gave, the credit industry has a positive feedback loop there.
Yes.
To get credit, I need to have credit in the first place.
Yes.
That's a very, very, that notion of bias is already there in the real world.
Yes.
Right. So, would you be able to?
Yeah. So we'll see how sort of an explore-exploit strategy works on this problem. But this is a sort of fancy problem because this problem is actually literally a one-arm bandit problem, like you have seen slot machines in casinos, right? So the goal is that let's say there are 5 slot machines and I want to pull the arm of each slot machine, and each time I pull, I see a reward. And over time, I should learn to find the best slot machine that maximizes revenue. So here you can choose to explore because, well, it's just pulling the arm, right? In real world, you cannot choose to explore. I cannot randomly pick a candidate and give a loan, right? So there are all those implementation issues, but at least this example that I'm going to talk about will serve to illustrate some fundamental properties of how fairness can come in the way of accuracy, and how accuracy can come in the way of fairness.
But we do these kind of things in real world also, like A/B testing.
Right. Sure. Yeah, that is an example. Okay, so we will look at the sequential decision-making problem. This is a machine learning. This is the classical machine learning problem. In the sense, this happens over several rounds. So typically, it's posed as a game between the player and the nature. The nature is the sort of adversary. And at each step, the learner or the algorithm receives a context. It observes some properties of, let's say, if it's a slot machine, it knows, okay, the slot machine has these properties, and I'm going to play the slot machine. And there are several things I can choose from, and I want to execute one of the actions. I want to execute one of k possible actions. And after I do this, I see a reward. So in the slot machine example, you see, let's say, you get money. Okay, and again, we want to illustrate 2 goals. One is a learning goal. So you want to be performant with respect to the task you have. Let's say you want to make more money. And there is a fairness goal. You also want to operate in a strategy that does not violate some discriminatory constraints. Okay, so let's look at this problem from the context of Uber. So let's say Uber is in the initial days of its business, and let's say there are k cab drivers, and the cab requests arrive sequentially, and the goal is to assign one driver to each request. And what is the reward here? The person goes into the app and gives 1, 0 through, or maybe 1 through 5 stars. And for now, let's forget that there may be this demand, the supply issues. Let's not. These are initial days. That let's say because rarely cab requests arrive, and there are enough cabs always. Okay. So the rewards are naturally stochastic, right? Because let's say there are 5 cab drivers, and each driver has some distribution over the rewards that in the real world, which you cannot observe. And why is it stochastic? Because it's stochastic because the way I rate the driver can depend on my mood swings, the time of the day, and the driver's rating can change depending on the geography. The driver may be familiar with a particular route over the other route, and there's inherent randomness, and there is biases. For example, if your application starts with 5 stars, I might always be lazy to click the 5 stars rather than go down, scroll, and click the first star. So there are all sorts of biases and randomness in the real world. And let's say this distribution captures all sorts of randomness, and there is a distribution over rating for each driver, and you do not observe. And let's say these distributions are fundamentally, you have absolutely no knowledge of the shape or any first order or second order, any properties of distribution. And Uber, let's say, wants to maximize expected rating over time. So that's the learning goal for Uber. And so let's say let mu sub I denote the unknown mean rating of drivers. So this is according to the real world, which you don't observe, right? And so what is optimal? So let's say you do this. Let's say cab request arrives sequentially, and after t steps, the best you could have done is mu star sub times t. That's the maximum rating you could have accrued, because mu star is the best driver that you in the real world. So if you always assigned all the cab rides to the real world to that person, you would have ended up with a rating approximately mu star times t, because mu star is the expected rating for the driver. So approximately mu star times t is your reward after t steps. And of course, you do not know what mu star is. So the best you can do is you will have some payoff. You choose some strategy, and you assign cab drivers, and the users, you got the feedback of the users, and the algorithm had a payoff. So you have regret, the best possible value minus what the algorithm has. And the goal is to design an algorithm that minimizes this regret. So the problem is clear? So this is, as I said, this is a classical, well-understood problem. There are several results around for this very, arguably very simple problem, and several variants of this result exist, several variants of the problem exist. For example, if you knew the reward distributions, you can have better results. But if you're completely agnostic to the rewards, then we'll see what sort of results are possible in this setting. And typically, this notion of sublinear regret. Sublinear basically says that over time there is a mu star t minus your payoff that you accrue. And let's say you look at the per step regret over t, like you look at the average regret, and you want that to go to 0. Otherwise, you're not learning, right? Because all trivial assignments can also lead to some reward, but you want a goal that basically is that you want to approach the best regret that you can. So you want this sort of a nature where as t tends to infinity, your per step regret, the average regret, should go to 0. So that's a natural goal. That's the learning goal that we have. And so one simple strategy you might think of is, let me get empirical mean ratings, right? So I can assign a few rides to each driver, and I can get, over time, I can see what the empirical rating is. And I can now, let's say, after, 100 steps, let's say I've converged on these empirical ratings, then I might say that, okay, this person seems to be the best driver. So let me try and assign all my future rides to this person. But this one does not work, because you may never be able to confidently say with any finite prefix data that this person is the unique best driver. So it's a very fundamental problem. It's a law of large numbers. You can show that even if you allow for a very large horizon where let's say you give 1 million cab requests to each driver, and you take the average, and then you cannot be reasonably confident that you've absolutely converged on the best driver. So this strategy does not work. So the whole point of this slide was to sort of convey this idea that exploitation can only help so much. Exploration is critical. So you should always err on the caution that you may have missed out the best driver just because the person did not get a chance to get enough rights, right? So here's a simple randomized explore exploit strategy. All these keywords are essential. It's a very simple strategy because it's easy to explain, it is easy to implement as well. And it's randomized because you can also have deterministic variants of this algorithm. But randomization also sort of succinctly gives the schedule without explicitly writing out the schedule, because the entire scheduling is hidden in the randomization. And it's also explore exploit because explore is key to the algorithm. So, and many algorithms in this field of online learning will have this flavor, randomized explore exploit strategy. And what is the algorithm? The algorithm is, as I said, is very simple. With very, very small probability over time, I will choose uniformly a driver at random. That's my explore strategy, because I also want to make sure that I give chances to drivers that I may have yet to realize the potential of. And with overwhelmingly high probability over time, I'll try and exploit the best driver I have with me. And I sort of engineered this number, square root of t, because I want the final regret to be 1 over square root of t. And this is not a unique. You can get any sublinear, like t to the 2 over 3, t to the 4 over 5. You can use all sorts of numbers, but you can show that this square root of t is optimal in a particular sense. Let me not get into that, but you can get a sublinear regret. So this algorithm basically makes sure that over time you will approach the optimal regret under the distribution. And so here, if you have k drivers, then actually this scales with k. Of course, if you have lots of drivers, then naturally you have to explore all of them. So there is a natural cost you have to pay in terms of the number of drivers you have. And let's say now, so we know that there is an algorithm that can give you a good strategy for optimizing for, let's say, revenue or accuracy, right? Now, let's say Uber also not only wants to maximize ratings, but also wants to assign rights in some fair way. Let's say that's its goal. And what could be a reasonable fairness criterion? This is here we focus on the individual fairness. And informally, it's very simple to say. Like if there are two drivers, one is better and the other one is worse, the algorithm should consciously make an effort to give the right to the better driver and the worse driver. So this is a very very fundamental unbiased notion, right? So I'm not, for example, stipulating anything about how the data might arrive to you. For example, you may never have enough data to judge whether the driver is worse or not. The data might be unfair, and the algorithm may not be able to make. You may even be able to prove that this algorithm has no enough data to make such a constraint. But I'm sweeping all those things under the rug. But I'm saying that this is my notion of fairness, and can your algorithm meet this notion of fairness? And for example, what is a true quality? In the real world, there's a true quality, and for us, it's just the expected rating under the distribution. So note that this is not revealed to us, right? None of this is revealed to us, but we still want to develop an algorithm that satisfies this at every assignment step. So formally, this is the statement we want to make. Whenever the algorithm makes a driver assignment, so at each step t, I want this to be true. If the true potential of the driver is better than the other for every pair of drivers, the algorithm's likelihood of assigning a right to the higher potential driver should be at least as large as potential, as the likelihood of it assigning the right to a lower potential person. For example, in the banking analogy, this could mean that if two people walk into the office with the same repayability potential in real world, then no matter what their applications say, no matter how they look, you should always be able to choose the person with the better potential for sanctioning the loan. So that's the natural requirement. So, okay, some simple, straightforward inferences we can make. The optimal policy is fair. What is the optimal policy? We know that optimal policy is one that we cannot execute, that always picks the best driver. That is fair because by definition, mu star is the best, so it's fair. On the other hand, you can have a trivial policy which always chooses a driver uniformly at random. That is also fair because the expectation is 1 over k, and it's all 1 over k, so you never violate that constraint because of the equality.
Less than equal.
Yes, the equality, so you're saved by the equality. But then this constraint, this particular scheme is not nice because it is in direct conflict with the learning goal. Uber may not make money with this scheme, right? And perhaps it's also in conflict with other notions of fairness. For example, As I say, the truly best driver may not find this prospect amusing, right? If you always assign rides, let's say in a round robin fashion. So let's revisit the algorithm that we just saw and see if that is fair, right? So that's a natural thing. This step looks reasonably fair, right? There's nothing that says that this is unfair. But I'm worried about this step because of the same reason that, especially in the initial few rounds, you may have no idea. Two drivers potentials could be arbitrarily close, and you may, just by the draw of the day, you might be choosing one particular driver over the other driver. So you might be violating this fairness constraint for a large time horizon. So that way, this algorithm is not fair. And so we can think of a slightly different algorithm. The real problem is that you never have a very good, at least in the beginning, initial phases, you will not have an accurate estimate of the mean rating. So it helps to maintain a confidence interval around your mean rating. So this confidence interval is a very simple statistical Chernoff bound type confidence interval that you can maintain. And so initially you will start with large confidence intervals, right? Because you have absolutely no idea where the actual means of the drivers are. So initially you will have really large ones, and then over time your confidence interval will start shrinking, and let's say you arrive at this phase, right? So here you can be reasonably confident that I can drop these two drivers out of the assignments, and I can choose from one of these three, right? But why one of these three? So because my fairness says that these two mu's could be ordered anyway because of the confidence interval, I have to make sure that I assign rights fairly between these two. And also the fairness says that because these two drivers have confidence intervals that overlap, I have to be fair between these two. And by transitivity, I have to be fair between all the three. So I have to uniformly choose. There's no other strategy for me but to uniformly choose between these three. So the algorithm is very simple. Let's say these are my estimates at step t minus 1, and I want to make a decision for step t. The way I will do it is that for these three, among these three, I will choose one uniformly at random with overwhelmingly high probability. And with small probability, I'll choose the other one. So this is the algorithm that you have. And this algorithm can be shown to be is probably fair according to the fairness constraint. Well, there's one caveat. So it doesn't satisfy at every step. With arbitrarily large probability, you can show that this algorithm is fair at every step. Why is that arbitrarily high probability? Because you may have completely adversarial draw on the day, and your confidence intervals could be way off, that there's no way you can guarantee any of these things. So that's the only catch where you have this arbitrarily high probability. But if your confidence intervals are representative, then at every step you will maintain the fairness goal. Arbitrarily means that you tell me, like let's say you tell me, with 99.9999%, I want your algorithm to be fair. Then I'll give you parameters such that it will be fair for that.
And is this the best we can do?
Yes. So let me complete the thought. So here you can show that the regret is k cubed over t. So what is the point? Remember that without fairness, you can get square root of k over t. Two points. One is that with respect to time horizon, I'm not punished at all, right? Whether I'm fair or not, I will take the same time horizon to converge. But there is a cost you pay in terms of the number of drivers. If your number of drivers is large, then because of this confidence chaining rule, you end up spending more time in exploration. So that's the only cost. And to answer Monoj's question, this is tight in the sense that I can show a distribution where the regret is at least square root of k over t if you ignore fairness. And I can show a distribution where you can satisfy fairness and your regret is at least square root of k cubed over t. So that's the reason I chose this example, because it sort of brings out the fundamental trade-off between fairness and accuracy. Yes?
Why on a certain date would the intervals be different?
Yeah, because let's say in reality let's say there are only two drivers. Okay. In reality, let's say their actual true ratings are epsilon apart in real world. Then there is no way that my confidence interval can capture this epsilon if on that day if on a particular set of draws or cab requests that come to me do not convey this information.
These confidence intervals are typically over a month. I mean, over the continuous time period, they are
Right. So see, all these confidence intervals also require some parameters, right? I cannot get a confidence interval over the entire. Like I cannot, for example, this confidence interval will be trivial if I say that the mean is 2, but the confidence interval can be anywhere between 0 and 5. So that's not a valid confidence interval, right? So that's why you need that arbitrary notion.
The other question is, can you give some idea where this 3 comes from?
This 3?
Yeah.
I have no idea. I mean, I think it's. I mean, the intuition is because of this confidence chaining, but I don't know why it's, for example, cubic and not quadratic. So.
Why do the confidence intervals continuously decrease over time? Like if you have an adversarial.
Again, by law of large numbers, right? Because if I give enough samples to a particular driver, then over time I will have more confidence in the mean rating of the driver. I should not come with it. One final point is that you can again extend these notions of individual fairness to notions of group fairness or statistical parity. So we can slightly change the game. So let's say instead of k drivers, there are k communities of Uber drivers, and at each day, one person randomly from the community shows up at work, and you want to be fair to that person. Again, what are the challenges here? For example, a community can be completely underrepresented, and a person may hardly show up from the community. But the day he or she shows up for the work, then you must be fair to that person, which might seem impossible, right? But then there's recent result that will be appearing at ICML from the same set of authors, Michael Kearns, Aaron Roth, where they show that very similar notions of regret, fairness, and algorithms can be extended to these notions of group fairness, where I will ensure that if there's this person from this community who has higher potential than another person from another community, then I will obey this ordering in my request assignment. So, and then now Praneeth will give a talk on, I think this will be the concluding part of this talk, on how you can mitigate some of the biases in NLP tasks.
So, I guess most of you should already know word embeddings, and you might already be using word embeddings. So let me just give a one slide summary of what word embeddings are. Basically, so you take a huge corpus, and then word embedding is basically will be an algorithm that embeds each word, corresponds each word into a high dimensional vector space. Usually the dimension can be thought of as 300. So you take each word and you embed it as a vector in 300 dimensions. And the idea is that semantically similar words such as sports is closer to game than to an exam and things like that. So hopefully you actually get numerical representation of each word, and then you can apply standard machine learning algorithms to these representations. So that's the idea. And of course, it's also widely used in several downstream tasks. Once after all, like word2vec and all these things have been made publicly available, they are very widely used in all these tasks. Yeah, so two examples of these are word2vec and Glow. So it turns out that these word representations actually have some very nice and intriguing properties. For instance, that things like some of the differences that we think semantically turn out to be like linear, have linear relationship in the word embedding space. For instance, man, woman, man. So if you take the vector man and the vector woman, and you take the vector king and the vector queen, it turns out that man minus woman is approximately equal to king minus queen. And similarly, people have looked at like verb tense and also country and capital and a bunch of relationships. And it turns out for many of these, it seems like the differences are actually captured by just a linear subspace, right? So in light of this, so what I'm going to do is we'll cover basically this paper which was in last NIPS in a workshop, and I really like this paper. And basically what they show is that they demonstrate how gender stereotypes actually exist in word embeddings without actually, like, just you learn these word embeddings and it turns out that gender stereotypes actually exist in these word embeddings that word2vec learns. And they also propose a way of overcoming that, and then we'll conclude after this one. So let's start with a simple example. So you take the he minus she vector. So this intuitively should correspond to something like male minus female kind of thing in the word embedding space. And then you project you take a bunch of occupations and you project things onto this line. Things that have very high positive inner product will be will be in the extreme he occupations, and things which are extremely low on the space will correspond to extreme she occupations. That's what we call extreme she and extreme he occupations. So it turns out that if you actually project all these kind of embeddings onto the he she space, it turns out that the extreme she occupations that the word embeddings return are basically, they correspond to homemaker, nurse, receptionist, librarian, and socialite, hairdresser, and all these things. And the extreme he occupations on the other hand are maestro, skipper, protege, philosopher, captain, architect, I don't know. So we can clearly see that these correspond to some of the real world biases that we actually have whenever we think of occupations which are more male and occupations which are more female, right. So this was one small experiment. So okay, so this basically corresponds to direct gender bias that we can see when we project onto this, because we are projecting directly onto male minus female or he minus she kind of axis. If we do the same experiment but onto something like football minus softball, where football we think of as more of a male sport and softball more as a female sport, we again get these kind of answers, where closer to softball we again get like bookkeeper, receptionist, registered nurse, and waitress, and so on, whereas the ones closer to football turn out to be again like businessman, pundit, maestro, cleric, and so on. So you can see that there is a correlation between the she occupations that we saw in the last slide and the softball here, and the he occupations in the last slide and the football here, even though football and softball do not really encode any kind of gender. So this is what they call indirect gender bias. So there is one which is direct gender bias, which directly comes from the like the fact that he she encode like male and female, and there is indirect gender bias which come about as a second order effect, which is between more male dominated occupations and more female dominated occupations in these word embeddings. So I will present just one more small experiment from their paper, which is basically they try to get she he analogies, and they get a bunch of analogies and they classify them into two parts. One are actually gender stereotypes and the other ones are gender appropriate. So gender appropriate she he analogies are basically like queen, king, sister, brother, where the gender is already intrinsic, like by definition there is gender in these definitions, whereas the analogies that turn out to be gender stereotypes are, for instance, like registered nurse and physician, and cosmetics, pharmaceuticals, housewife, shopkeeper, nurse and surgeon. So the point is the occupations do not really encode any kind of gender. However, it turns out that when you ask for these analogies, it turns out it gives occupations which seem more female and occupations which are considered more male. Yeah. Okay.
And women like cupcakes and men like cake. It's like men never giggle.
So I mean, at one level this might actually seem kind of easy to okay. First of all, what is the issue with having these issues in word embeddings? So clearly word embeddings, as I said, are used in so many downstream tasks that it can actually have huge impact in terms of how it interacts with say even male related words and female related words, and this might end up actually even perpetuating these kind of gender biases based on how these systems are used. Yeah. So they used on Google News. So I think so. They said it's publicly available. So they trained word2vec in 300 dimensions on Google News corpus. I don't exactly know how big of the corpus it is. So I think it was the last year or so. Oh, I don't know. Okay, so they did the work in the last year because I know them, but I don't know what span of Google News they actually use.
It can be like 1800s or 1900s.
Yeah, it has to be.
It will be last 10 years max.
2013-14, I think, the Google was 1.7 billion worth or something.
Okay. So they mentioned that this is actually publicly available, so I don't think they even trained this word embedding. The word embedding was trained by Google and made publicly available by Google as well. Okay. So clearly we understand that this is actually very important even in the systems that we build, because how we use like the stereotypes that are encoded in these embeddings end up just creeping up into the applications that are built on top of them. But what is the challenge? The challenge turns out to be that word embeddings are actually surprisingly effective. And what I mean by that is that, for instance, nurse occurs more frequently with a male, because whenever someone says a nurse, if it is female, they just say nurse. They don't say whether it's female or male. But when it's a male nurse, they explicitly say male nurse. So if you look at the co-occurrence of nurse with male and female, it occurs with male much more often than with female. So if you just thought of word embeddings as co-occurrences, nurse should be associated with nurse should be associated as a male profession. However, word embeddings know that it's not really a male profession; it's a female profession from data. Yeah, and similarly, like quarterback and male. So female quarterback appears much more often, and male quarterback you almost never see. But still, word embeddings think of quarterbacks as more male than female. So this is the main challenge of dealing with these systems in word embeddings.
Because when you say scientist, it's like just science.
Possibly, yeah. And similarly, actor.
Female scientist is probably women scientist is
Yeah.
probably
Yeah.
used to specify. So in that case, it causes an issue.
Yeah. I mean, surgeon or scientist, all these cases, I think so, yeah. Okay, so.
Pronouns which cause this.
Yeah. So all I'm saying is that they have much more knowledge of the surroundings than just the adjacent words. So that's the main challenge of dealing with this. So the approach that they basically suggest is to first concretely establish that there is this gender direction, and then establish that there is this gender bias that actually exists in these word embeddings. And then they also propose a method of bias correction, either hard or soft, for gender neutral words or gender neutral occupations that you don't want to have this gender bias. So I should, like, before even I go into this, I should mention that, like, all of this paper is just last December, and all of this is like extremely evolving area. So, and there are no solutions or anything. So there are a lot of open questions and directions in this area to pursue. So the first thing that they try to do is basically, what is the gender direction? How do you find it? And you could think of many different word pairs that would give you this gender direction. Examples are, you could take the male female pair and then look at the vector, which is male vector minus female vector. Similarly, you could look at he vector minus she vector, or lot of other pairs that you can see, that you can think of, and then you can look at the differences, and that would intuitively give you this gender vector. However, not all of them are exactly equal. Even though they have been shown to be approximately equal, they are not exactly equal because of both the sampling issues and accuracy of your networks and so on. And the solution that they propose is to basically stack all these vectors in a matrix and take the top singular vector or top singular subspace of this matrix, and that somehow corresponds to the gender direction. Okay.
So they define these vectors, male
Yeah.
minus female, father minus mother, etc.
Yeah. So for all of these, they actually also use Amazon Turk crowdsource. So they do crowdsourcing to figure out what are the things that people think are more representative of gender. So they do a crowdsourcing to get opinions of people. So they give a bunch of options, and they figure out what of these intuitively do people think captures the gender direction a lot, and then they take those vectors, and then they find out the top singular vector or top singular subspace of this matrix, and that intuitively should correspond to the gender direction or the gender subspace, right? And so if you look at the singular value,
Any one of these,
So any one of these, so there is no reason to pick one over another because all of them should intuitively be the same, but it turns out that they are not exactly the same. So you somehow have to average all of them to get something which is much more accurate. So what they do is they stack all these vectors together and take the top singular direction, or you can take more general top singular subspace of this thing, of this matrix, and that you can call either the gender direction or gender subspace.
That subspace is of what size?
So in this case they pick just one vector. So it's of dimension 1. So you could in general pick 2, 3. So these are all maybe more practical questions. Okay. So one of the explanations that they say why this, like taking the top singular vector here actually makes sense is if you look at the singular values. So the left one is the singular values of the matrix that we saw here. So this matrix, you plot the singular values, then the left plot is basically the singular values of this matrix. The right one is what you would see if you had a random matrix of the same dimension and same norms. So clearly in the matrix that we constructed, the top singular direction is much more significant than if it were random. So somehow this actually is encoding some information. So intuitively this seems to suggest that you can basically look at the top singular direction and that somehow corresponds to the gender direction. So this is basically the motivation for why we are even looking at this top singular direction and why it makes sense at least in this specific word embedding scenario. Okay, so now once we find out this gender direction, the question is how do you do this hard or soft debiasing of all these gender neutral occupations or gender neutral words, and the algorithm is actually fairly simple. So let's say B is the gender subspace that we found out using the previous step. In this case B could be just a single vector, so one dimensional subspace, and for the hard bias correction we take any gender neutral word, maybe something like a scientist or a surgeon or whatever occupation where it does not have any associated gender. We can set we can basically remove the component along the gender subspace and make it just orthogonal to the gender subspace direction. So WB corresponds to the projection of W onto this gender subspace, W minus WB is the orthogonal component, and then you basically normalize it. So you can re-engineer these word embeddings or modify these word embeddings to remove this gender component for these gender neutral words. And a soft bias correction would be, instead of doing this hard correction, you want, so you have two different terms. So first of all you want to, okay, so W is the word matrix, N are the gender neutral words, and T is a linear transformation that you want to find, where you want to transform this word embedding from W to TW. And what are the properties that you want to satisfy? The left, so you want to minimize this whole thing. So there are two parts to this. So the left part is basically saying that the inner product of any two different words should be similar before the transformation and after the transformation. So TW transpose times TW gives you the inner product after the transformation, and W transpose W gives you before the transformation. So they should be close. And Tn transpose Tb is basically, Tn is the transformed gender neutral words, Tb is the transformed bias subspace, and they should be orthogonal. Okay. So in the hard case you basically completely remove the gender bias subspace, and in the soft case you want to retain the utility of the word embeddings while at the same time minimizing the bias component of the gender neutral words. Okay. So basically they provide a few more results on what, like on both of these algorithms for hard bias and soft bias correction for the word embeddings, to show that first of all, if you do the same kind of experiments, so here we did, so if we do both these gender stereotype experiments to get she-he analogies as well as projecting occupations onto the he-she axis or softball football axis, it turns out that they are much more fair in terms of gender as compared to what they were giving before we did this debiasing, right. So Okay, so the first one is that they empirically show using Amazon Turk's crowd sourcing that after they do this debiasing, the gender stereotypism in the word embeddings has been reduced, and it's still useful. It's not like you have removed all the information completely, that the word embedding is no longer useful. So it satisfies both these properties on certain tasks. And they, yeah.
Do they show that on some tasks the fairness is improved because of this? Not the analogy task, but some other real world task.
Real world tasks, they don't.
Like a CV,
No.
Guessing the gender of a CV or something.
No. I think, are there any standard data sets for evaluating on those?
I don't know.
So I think because of that, I think like evaluating them might be much more challenging, and even for these they had to do crowdsourcing, and if it's more like resume, which is much more complicated, having an established data set might be immensely helpful in doing this. Okay.
I don't think that is a well defined task. I just made it up.
Yeah, the fairness aspect is not clear. So I mean, there are a bunch of further questions even in just in this context. For instance, how do you handle not just a single bias of gender stereotypism, but say caste, religion, and region, all these different aspects. And if you start doing one debiasing for each of these things, at the end of it, you might actually get something which has no meaning whatsoever left in the word embeddings. So how do you incorporate all of these things together and do the debiasing? So that's one question, and they only do this for English, and doing it for other languages might be either easy or challenging depending on the structure of language. If the language structure is quite different, where like male and female are automatically included in the way the word ends and things like that. So like scientist is basically a gender neutral, but maybe when we say that in Hindi or Indian languages, maybe most of the occupations also end with like a male or female form. So
Yeah, I mean, for maybe, like after diminutive is also feminine. So when you say the use the masculine ending dabba, you mean a big box, and when you say dibbi, which is like a small one, then it is a feminine. So like some of these things are just entrenched in the language, and I don't know how it's
yeah, I don't know. So I think this paper actually raises very interesting questions, and before okay, so let me start with actually before this, let me point out another paper that I read recently, which I found extremely interesting in the context of gender bias in word embeddings. Is not even gender bias, or most of the biases that we have in our mind. So people, okay, psychologists do something called implicit association tests, where basically you are given two things, let's say hard and soft, and then you are given a word, and then you have to put this either in the hard bucket or in the soft bucket, and the reaction time that a participant takes to actually do this somehow is indicative of how strongly this word is associated with that particular attribute or adjective or whatever, right? And what these guys, not this guys, but some other paper, what they did was basically to have a bunch of these words, look at word embeddings of these things, and see and measure like angles between these words or distance between these words, and figure out how. So in traditional psychology, people have figured out a bunch of implicit associations that people seem to have based on experiments on humans, right? Based on these implicit association tests. And what these guys did was basically they did a similar experiment on word embeddings, which is generated from a corpora, and verified whether similar kind of implicit association also exists in these word embeddings. And it turns out that even many of the implicit associations that we have in our minds also turn out to exist in these word embeddings. So it's actually a very real thing that whatever biases that we see in the world and around us actually end up in these systems, and it's important to take account of them. So let me also briefly mention what are all the other approaches that have been tried. So I would like to claim this. Hopefully, I'm not being recorded, but I think okay. Okay, so all the let me put it this way. So all the approaches that I have seen so far, I think, can basically be captured into these 2 or 3 buckets, and these are basically all the kind of approaches that I have seen for ensuring fairness in machine learning systems. So the first one is that you have a constraint. Naga presented a bunch of fairness metrics. So you put whatever constraints you pick and whatever protected class you pick, and then you put that constraint as a constraint in the optimization problem, and then you solve that optimization problem. So that's one class. And even within this, you could actually take an existing predictor where you don't write a completely new optimization problem. You take whatever is available for you and then massage it to satisfy these constraints. So in the supervised learning setting, basically these are the 2 kind of things that I have been able to find in literature in terms of what are the approaches that people actually have come up with for fairness in supervised learning. For unsupervised learning, on the other hand, people the one thing that I have been able to find is basically that people want to find embeddings that actually do not encode information. Defining this is quite tricky. How do you, so eventually, let's say you want to do some supervised task, you go through some features. So you have this input data, you want to find another embedding of this into some other space, and then you use whatever classifier on this one, and then you want to encode this into the space in such a way that the encoding does not actually capture any information about either gender, race, or any of the protected attributes in the original space. So broadly, all I wanted to say was that this area has just started, and at the same time it's extremely important. So whenever you are building a system, if you could just think about what are the fairness questions that might pop up into your system once it's actually out in the real world. If you could just pay a little attention to how are the ways that you could possibly tackle it, I think it will be extremely useful both for your system and for the community as a whole. So with this, I just want to leave you with some resources, and that's all I had to say. Yeah.
Two couple of comments. One is this term fairness is generally associated with a judgment, right? And what is fair to me may not be fair for you. It's a very judgmental thing, and I generally associate bias as more like a machine learning technique. So fairness is more like a human perception of what the data is out there. And second possible comment is that many a time you want these biases in the data for the algorithm. You want the algorithm to absorb those biases. So the machine learning, the goal generally is you want to observe the correlations and the bias that exists in the data to produce. And one of the comments you made in the word embeddings is that when you try to de-bias everything, you may not learn anything.
Yes.
Right. So there is a counteracting goal between the two.
Yes.
And often with the steps that you have described, some of them are just trying to regularize it to less overfit the data that you may see later. So is it fair to say that that it's a balance that you need to play with?
Yeah, definitely. I mean, even the talk that Naga gave. So whenever you try to enforce fairness, it's very much possible that you actually lose out on either revenue or accuracy or any of these, like these things that we actually usually maximize for. But at the same time, it's important for us as humans to enforce things which we believe in these systems rather than just to maximize revenue. For instance, if a person was actually doing this, it would have been wrong. So we cannot just blame an algorithm saying that it's coming from an algorithm and then we cannot take care of it, because in some sense I would also think that like machine learning probably also gives a way to remove biases in the society, because if you want to make people unbiased, then you have to change it. So as an algorithm, you have one thing under your control, so it may be more possible to change the algorithm.
I have another thing to what he's saying, like a slightly different point of view to what he said. is that, there's this whole notion that people have that because it's machine learning and it's all data based and therefore it is somehow devoid of biases and it is like the most neutral way of doing things. And that is something that I think people should really realize, that just because it's data based and you have a whole lot of data and the machine did it, does not make it unbiased. The data and the machine will have all the biases that are there in the humans. So, and how do you kind of counter that, and where you counter that and where you don't counter that is like the open question, right? How can you do this? But this whole notion of like a data-based approach being somehow superior because it is devoid of human biases is wrong, simply wrong.
Yeah, I mean, all of these basically establish that data itself has biases because of the way we have acted and then use that to generate data.